Ever wondered how fuel travels from the wings all the way to powering a jet engine? Let's break it down in the simplest way possible, from storage in the wings to precisely metered combustion, all the way to thrust. In most aircraft, fuel is stored inside the wings in sealed fuel tanks. Placing fuel in the wings keeps weight close to the lift, reducing structural stress and helping balance. Large jets use integral, or wet, wing tanks. Smaller aircraft may use bladder or rigid tanks. Internal baffles reduce sloshing, so fuel doesn't surge during maneuvers, takeoff, and landing. Vents and surge tanks manage pressure changes and thermal expansion at different altitudes. Transport jets also carry center and sometimes tail tanks, sequenced to maintain center of gravity. Fuel is measured by mass. Density varies with temperature, so systems monitor quantity and temperature. Low points with drains help remove water and contaminants during maintenance. Inside the tanks, electric boost pumps pressurize fuel and send it forward. Each tank typically has multiple pumps for redundancy, with automatic switchover if one fails. If all boost pumps fail, some engines can suction feed at low altitude, but performance is limited. An engine-driven pump then raises pressure further for precise metering and atomization. Cross-feed valves allow one side to feed both engines if needed to correct imbalances. Transfer pumps move fuel between tanks. Some jets have jettison systems to reduce landing weight. Pilots control pumps via overhead panels, while logic prevents unsafe configurations. Low-pressure lights and ECAM or EICAS alerts call out abnormal conditions immediately. Bottom line, boost pumps push, engine pumps pressurize, and crossfeed keeps things balanced. From the tanks, fuel travels through rigid and flexible lines routed along the wings and fuselage. Filters remove particulates, water, and microbial growth that can form in tanks. If a filter clogs, a bypass valve maintains flow while alerting the crew to service it. A fuel oil heat exchanger warms fuel and cools engine oil, preventing icing and improving efficiency. Some systems use water separators and additives to reduce ice crystal formation in fuel. Flexible couplings isolate vibration and thermal expansion between the wing and fuselage. Pressure, temperature, and flow sensors feed the computers with real-time data. Comparing quantities and flow helps detect leaks or imbalances early. Before fuel enters the combustor, a fuel control unit meters exactly how much the engine needs. It considers throttle lever angle, compressor speed, temperature, altitude, and power demand. On modern jets, FADEC computers command the FCU for full authority digital control. During start, the FCU manages flow to light off, then stabilizes idle without overfueling. When you advance thrust, it ramps fuel smoothly to avoid compressor stall or overtemp. At altitude, thinner air means different schedules. The FCU compensates automatically. Fuel nozzles atomize fuel into fine droplets for efficient mixing with compressed air. Duplex nozzles and manifolds maintain good spray patterns across power settings. Safeguards limit fuel flow if temperatures or speeds trend beyond limits. Compressed air exits the compressor and enters the combustor where it meets metered fuel. Swirlers create a stable vortex, forming a primary zone for continuous flame. Igniters spark during start and certain conditions, but the flame stays self-sustaining in normal flight. Dilution air cools and evens temperatures before gases reach the turbine. Modern combustors balance efficiency with lower emissions and cleaner burn. Disturbed airflow or fuel issues can cause flameout. Restart procedures and auto relight help recover. Exhaust gas temperature is monitored to keep a safe margin below limits. Combustion expands gases that accelerate through turbines and the nozzle. Mix, ignite, stabilize, cool, then extract work, without wasting fuel. Thrust is the reaction to accelerating mass backward. Newton's third law in action. In turbofans, most thrust comes from the fan's bypass air, with the core providing energy. The nozzle shapes and accelerates exhaust to convert pressure into velocity. FADEC links throttle requests to fan speed and fuel flow for predictable thrust. Specific fuel consumption measures efficiency. Lower SFC means more thrust per fuel. Altitude, temperature, and speed change thrust available and fuel schedules. With the right mix and flow, engines deliver steady, controllable power for takeoff and climb. At cruise, precise metering keeps fuel use economical while maintaining speed. Pilots watch fuel synoptic pages showing quantities, pump status, and valve positions. They monitor totals and left-right balance to keep the aircraft within CG limits. Fuel pressure and temperature trends hint at pump health and icing risk. Dispatch plans legal reserves, alternates, and contingency fuel before every flight. If an imbalance appears, cross-feed and transfer procedures correct it methodically. Alerts like fuel low temp or fuel imbalance trigger checklists and limits. Fire detection loops and engine shutoff valves isolate fuel instantly during emergencies. Bonding, grounding, and lightning protection prevent sparks and arcing near fuel. Regular sampling, filter changes, and inspections keep the system dependable. Turbines burn Jet A or Jet A1 kerosene. Piston aircraft use avgas with different properties. Quality checks verify density, water content, and contaminants before fueling. At cruise, cold-soaked fuel can approach freezing. Heaters and routing mitigate icing. During fueling, bonding cables, proper labeling, and sample drains reduce risk. Fuel weight affects takeoff distance and climb. Dispatch optimizes load for the route. Study the synoptic and QRH fuel pages for your aircraft. They explain logic and limits. From wing tanks to precisely metered combustion and thrust, that's how fuel keeps aircraft flying. Follow for more aviation insights and ace your next systems exam.